this. It doesn't have to be like this. It doesn't have to be like this. Killer whale, killer whales. All right, all right. We're here with our final lesson before Thanksgiving break, and I think it's going to be a good one. That was cheesy. All right, all right, all right. We're here with the last lesson before Thanksgiving break, and I feel like every time I say the same kind of thing in the beginning of the video, like I'm relieved something is happening or whatever, but yeah, I am relieved that Thanksgiving is coming up, and that I think the past 3 probability lessons have been really good, okay? So historically, I find probability really difficult to explain, but I think we're crushing it so far. And even though we're not going to finish the unit before Thanksgiving, we're in a really good place. Okay, so this is, I think, the hardest of the 3 lessons, but I think it's probably the most fascinating. And whenever we're doing probability, I think that your approach here has to be to really understand the logic of every question. Okay, because probability, the math is so easy. You just have to understand exactly why you're multiplying and adding, et cetera, et cetera. So yeah, here's our lesson, and we will have a quiz released as well after this. We're starting with a reference, and I was just going to put the answer here to leave it, but I think that we can do it really quickly together. And the distribution we draw, the little diagram we draw, is going to be kind of the basis for the rest of this. It was a warm-up because we're rolling a 6-sided die, which we've done every lesson so far in probability, and we're answering things we've definitely done before. First, it says if you roll the die 1 time, what is the probability you select a 3 or 4? And the gist of this is we know that there's 6 outcomes of the die, right? And I'm going to draw it at the same time. 2, 3, 4, 5, 6. So there are 6 possible outcomes, and it's just saying how likely is it that it's a 3 or a 4? And we know that each of these outcomes, because the die is even-sided, has like a 1/6 chance, right? So if I wanted the probability of you roll the die and you get like a 3 or a 4, we know that all we have to do is add those probabilities together. Okay, so if there's a 1/6 chance you get a 3 and a 1/6 chance you get a 4, it's a 1/3 chance that you get a 3 or a 4. We know that that's for a single event, right? Rolling at 1 time, but we can do events in succession, right? So if we roll the die twice, we know that if we have separate events, we multiply their probabilities together. So if you wanted the probability that you want to get a 3 or 4 both times, think that the first time you did it, there was a 1/3 chance. But for that 1/3 chance outcome to happen again, that likelihood is not that much. Think that it's 1/3 of 1/3, which is 1/9. And all I want you to see is that the 2 basic things you do in probability are you add if you see or, and you multiply if you see like 2 events, even though it says or here as well. But we're going to try to expand that by returning to a deck of cards, which is a great probability example. And we'll start with something we could do again. So it says for A, if you select 1 card from the deck, what is the probability you select a 9 or a 10? And this is very similar to what we just did, right? We know that 9s and 10s are separate from each other, right? There's 4 9s and there's 4 10s. So there, if you were to pick 1 card randomly from here, just think like you put your finger randomly somewhere, the chance that it's a 9 or a 10 is just 4 plus 4 out of 52, or the total, right? Which is 8 out of 52. We can't do that one in our head like the other ones. And hopefully what you see is that this kind of looks like a probability distribution, right? If we want the chance of a 9 or a 10, it's this row plus this row. Okay, so you could shade them both and it's this much of the whole. The problem here that makes probability more difficult is that, we could ask you things about decks of cards where the two things we're asking about aren't going to be completely mutually exclusive or separate from each other, right? So this hopefully makes sense to a lot of people, but this is where we complicate it. For B, it says, if you select one card from the deck, what is the probability you select a heart or a face card? So if you were gonna do this the way you would have done all the old questions, you probably would figure out the probability of a heart, which is 13 out of 52. And then you would have figured out the probability of a face card, which is 12 out of 52, right? And all that is to say that there's a 25 out of 52 chance, or almost half the cards are either a heart or a face card. And you can pause to think about why this isn't gonna work. But the idea is that some of the hearts are also face cards, right? These 3 cards. So if I were to just count how many outcomes are hearts or face cards, I think we have these 10 cards plus these 12 cards. So there's 22 cards that are a heart or a face card. But if we just added up those probabilities, 13 plus 12, it gives us 25 because we're double counting these 3 cards, okay? And hopefully that makes sense to everyone. And all that is going to do to our probability formulas is that what we have to realize is that if we add up probabilities, we can only add them up if they have no intersection, okay? And an intersection is cards that they have in common. So instead of drawing a distribution like this is where we start drawing Venn diagrams, which you've definitely seen in life, but maybe you haven't seen in math. So think that if this is all the cards in the deck, there are face cards and there are hearts. But then there are cards that are both face cards and hearts, okay? So if you ever see a Venn diagram in probability, it means that some of your outcomes could intersect, okay? You could have both and you could have neither, right? There are a lot of cards that wouldn't fit in either of my 2 circles because they aren't a heart or a face card. Here, the rest of this we're pretty much, and I'm gonna zoom in, so we'll have to wait a second. Excellent, I've actually figured out I could press focus and that stops anyway, so that's awesome. But yeah, what we're gonna do is we're gonna draw a Venn diagram to describe the situation. So think that there are 13 hearts, but 3 of them are also face cards. So the intersection goes here, there's 10 hearts left, and there's 9 face cards that aren't hearts, right? The other 3 suits. From here, there's a 4th component, and that's always what's on the outside. But once you recognize what the intersection is, if we know that there's 52 cards, that's just gonna be the remaining 30 cards on the outside, meaning they aren't a heart or a face card. So again, I think I explained it decently well, maybe not perfectly, but we can't always use just adding up our probabilities like 1/6 plus 1/6 unless the events are completely separate from each other, which we call mutually exclusive. And from now on, you'll see Venn diagrams and questions will indicate that there's an intersection and you have to be aware of that intersection. But I think that's really cool. And next week when we do, or after Thanksgiving, when we do more technical probability, we'll look at this formula more, but know that you can add probabilities up as long as you subtract by their intersection or the probability that they both occur. In this case, that was those 3 cards. So this would be 13 plus 12 minus 3. So that would be the probability, and we could find that percent as well. So if we're talking about what events are mutually exclusive means that if you are one of them, you are not the other, okay? You're only one. So 9 and 10 are mutually exclusive events because you can't be a 9 and a 10. There's no intersection between those two. And very quickly, if we were to draw 9 and 10, think that that's what the probability would indicate. There's a bunch of cards that are neither 9 or 10, but there's no cards that are both. Okay, so if you ever see a Venn diagram like this, which is pretty much, this, just drawn with circles, it indicates that the two events are mutually exclusive. Hearts, hurts. Okay, hopefully that makes sense to everyone. And for the rest of this, we're just going to draw Venn diagrams based on scenarios. So that's what the big practice of this is. So I don't think it's going to be too bad. For E, it just says draw a Venn diagram to describe the two outcomes, number cards less than or equal to 5, excluding the aces, and then spades. Okay, so if you're ever going to draw a Venn diagram, for now, it's always just going to have two circles, pretty much always. You want to identify the two events, which is less than or equal to 5, and spades. And the most important thing to find is the intersection, okay? So this question doesn't give us that information, but we know we're working with a standard deck of cards. So think that the cards that are 5 or less are these 16 cards. The spades are these cards. So there's 4 cards that are the intersection. And my drawing looks kind of awful, but I think it's not a big deal. Find your intersection first. The 4, the 2, 3, 4, 5 of spades. That leaves us 12 cards that are less than 5 but not spades. And then 9 cards that are spades but not 2 through 5. Then if you want to find out how much is not any of that, you could just add up and divide by 52 in this case. So let's do it in our head. 16 plus 9, 25. 52 minus 25. It's going to give you 27. So yeah, that's that. Let's continue on. We have 2 more examples. That's the big gist of it. Where we're going to transition though for these two, which is interesting, is that we're no longer going to talk about like traditional things you think about in probability, like a die or a coin or a spinner or even a deck of cards. We're going to apply that to other situations, right? Because probability is just how likely is an event to occur. And that event can be anything that doesn't happen all the time. So 2 and 3 are a situation where I'm randomly cold calling students in the class and we have some information about the class. Okay, so I don't ever cold call in real life because Senora Doreen kind of messed up my confidence in 9th grade because she cold called me every day. I was the worst Spanish student in the class. And from then on, I've had kind of like anxiety that teachers are going to call on me. So yeah, I don't ever cold call. I think that, you can listen and not necessarily be ready to present something. But yeah, imagine that I have my 40 students and I'm going to randomly select one of the students in the class. And we want to find probabilities of that. But the information I'm given are that some of my students are also in psychology and some of them are in computer programming. So 40 students, 25 are in psych, 20 are in computer programming, and 10 aren't in either class. So before we do A, actually let's read it. It says, if you randomly cold call one student, what is the probability that they're enrolled in psychology or computer programming? So this or means that they could be this or that, or even both of them, right? I'm picking on a student that's enrolled in one of these classes. But to do that, we have to figure out how many students are in all of those boxes. So we'll make our Venn diagram. And in this unit, or this problem set, if you make the diagram, the questions become really easy. So the 2 outcomes or information we have about the students are psych and computer programming. And now we want to fill out whatever we can. The easiest information I'm going to tell you is always students that aren't in either circle and students that are both, okay? And the reason for that is think that there's 25 students signed up for psychology. So there's 25 students here, but we don't know if they're here or here. But we'll get closer to knowing that if we can figure out how many students aren't in either. So if there's 10 that aren't in either, this plus this plus this is going to have to add up to 30, okay? And I think I kind of didn't realize this was going to be a really hard question, but here's what I want you to think. We have 25 and we have 20. But if I add up all of my numbers, it's going to be way bigger than 40. In fact, it's 55, right? But if we put a student on the inside, that's going to result in less students total, right? Because you're going to double count these students. And what I mean by that is, let's just imagine that 10 students are enrolled in both. If I put 10 in the middle and I add up my numbers now, 10 plus 15 plus 10 plus 10 is now 45. So we've reduced the number by 10. If you put 10 students in the middle, that's going to mean that you have 10 less students to worry about. So what I want you to think is that, so think that at first, it appeared like there were 55 students because there's a 25, a 20, and a 10. But once we put 10 students in the middle, that made the total number 10 less. So all you have to do, if you ever want to figure out the intersection, but you aren't given it, is reduce this number and put that many students in the middle to get to your total, okay? And I know that I haven't explained this perfectly. I actually didn't even realize that I was gonna actually teach this right now, but think that there's 10 students here, 15 in the middle, and 5 over here. And again, I'll stress that this class is all about logic when we do probability. Think that this is gonna satisfy everything in my board problem. 10 students aren't in either, 25 are in psych, and 20 are computer programming. Therefore, 15 are the intersection, okay? So if it asks you, what's the probability that a student is in psych or computer programming, know that all we have to do is add up these numbers and then divide by the total. So there are 30 students out of the 40 who are signed up for at least one of those two classes. Let's keep going because I think that was difficult and I want you to feel more confident. For C, it says if you randomly cold call one student, what is the probability they're in both classes? So again, the key is that drawing the Venn diagrams can be the hardest part. But once you do, you just kind of have to add up what it's asking you. There's a lot of things it could ask you, right? But if it's saying both, that's here. And I think that's 40%. 0.375. Okay, and then if you randomly cold call one student, what is the probability that they aren't in computer programming, but are in psychology? So just another thing you could ask, they're in computer programming, but not psych. So it's not these students. And there's only 5 of those students in that case. Of the 20 computer programming students, 15 of them are also in psych. So like a lot of them. So only 5 out of 40 students would be the computer programming students, not in psychology. Probably the engineering students. Although this isn't like the most realistic breakdown of these classes anyway. All right, that's that. Let's tackle one more. And we're still talking about cold calling. I'll make sure this is an example for you too, but we're given different information. Let me just draw in my diagram to start. We have 35 students in class, 10 play football, and 3 students are on both the football team and in band. If 20 students participate in neither community, we're going to try to find some probability. So the 2 outcomes we're looking at here are football and band. And this one I think is actually going to be easier. 20 students participate in neither community. So 20 is a really easy number to start my Venn diagram with. There's 20 students on the outside. 10 students play football, and 3 students are on both the football team and band. So again, if you can find the intersection or neither, those are the best numbers to put in your diagram by far first. Because we have 10 students to play football, but you can never put 10 here until you know the intersection, or it tells you like these students play football but aren't in band. So those students go there, and then just think that there's 35 total. So if there's 35 total, add them all up, and band has to be the remainder. So yeah, I think that's good. Let's answer some of these questions. If you randomly cold call one student, what is the probability they're in band? So you couldn't just do 5 out of 35. Make sure you're doing both of these, even though it didn't say that, right? So there's 8 students in the band in my class, but it never tells you that, right? It tells you everything but that. And again, diagrams are the key to this class. Reading graphs. All right, if you randomly cold call one student in class, what's the probability that they're in neither? I don't even know why I gave you that. That's very easy. I think it's because D will be our last challenge. And yeah, the gist for, so D says, if you randomly cold call 3 students, what is the probability that they're all on the football team? And all I want you to realize here is that Venn diagrams just describe a single event, right? The outcome of me pulling one student, what am I trying to say? This represents if I cold call one student, how likely is that student to be in any of these groups or in either of these groups? But if it's asking about cold calling 3 students, just think that that's 3 events. And we just have to figure out that probability and probably multiply it by 3, right? And I actually forgot, I should have wrote, this is really important, without, like, I am kind of pissed at myself. Okay, so it's saying we're gonna randomly cold call students, and I'm gonna write on your sheet D and E for with replacement and without replacement, because think that creating the Venn diagram might just be the start of the question or what you have to do first. Because here, let's do them individually. What's the probability they're all on the football team? So for the first student I randomly call, there's a 10 out of 35 chance they play football, right? If it's with replacement, which in this case, if you think about it, would mean that I'm like a really cruel teacher. Like if I cold called you once, I would do it again. Heartless, okay? So if I'm replacing the student, putting them back in the set of students, the probability is gonna be unchanged. There's always a 10 out of 35 chance that I select a kid on the football team. However, if it was without replacement, which is what, a normal teacher would do, think that if I select a student on the football team, I'm not going to select that student again. So I would call on any of the other 34 students in class, and only 9 of them in this case will be on the football team, because the football kid is sitting pretty, they're done with participating. Hopefully that makes sense to everyone, because I think this is overall a really cool lesson and ties everything kind of together that we've done the past 3 lessons. This is really unlikely in both cases. Wait. So yeah, I messed up the first probability when I gave it to you, but those are the 2 probabilities. So even if you have a Venn diagram, it could ask you about multiple events. Just make sure you multiply and are aware of the difference between with and without replacement. So yeah, that's everything. I honestly feel great about this lesson, and I'm really proud of you for making it through. Yeah.